Welcome to the last screencast of our module on electrochemical thermodynamics. In this last screencast we will discuss the Pourbaix diagram. A Pourbaix diagram maps out possible stable phases of an aqueous electrochemical system. Now what does that mean? In practice it is something you can use to see whether, for example, a metal such as iron wants to be metal iron at a certain potential and conditions, or wants to be oxidized to, for example, iron 2 or to iron 3. So for that you can use a Pourbaix diagram. That's why it's used, especially in corrosion science, to indicate whether a compound is stable or dissolves into solution. And for that, to indicate whether it's dissolved, a concentration of 10 to the minus 6 molar is applied. Now, why is this 10 to the minus 6 important? That I will explain later. Now, in electrochemical engineering, we use Pourbaix diagram especially for electrode selection to get a feeling of whether our electrode material is stable under the conditions we apply. So the conditions are both the potential, but also the pH. So that then it's important to know how the metal we want to use in electrode material behaves. Now, a Pourbaix diagram can basically be constructed from standard electrode potentials, solubility products, and the Nernst equation. Now, to start playing a bit with the Pourbaix diagram, I recommend you to carry out quiz question 2.7. Now, let's look at an example of a Pourbaix diagram. You can see one here on the right. A Pourbaix diagram shows on the x-axis the pH and on the y-axis the standard electrode potential versus the standard hydrogen electrode. Now, what does it show? It shows all these basically areas where it lists the metal, the state of the metal. For example, here we see iron. This means that if, for example, you're at pH 4 and an electrode potential of minus 2 volts versus standard hydrogen electrode, your iron, its stable thermodynamic form is the metallic form. But if you increase the potential, for example, to 0 volts, the stable form is iron 2. So if you have metallic iron and you apply a potential of 0 volts at a pH of 4, you know there's a thermodynamic driving force for it to convert from iron into iron 2 plus. Does not mean that it necessarily immediately starts converting from iron to iron 2 plus, because that will also depend on the kinetics, but it indicates that there is a driving force. And so there are all these blocks that indicate this is the most stable form. And if you are in that form, it's likely to stay the same. If you are in another form at these potentials, at these conditions, then there's a thermodynamic driving force that wants to change basically the state. Now, how do we construct such a Pourbaix diagram? Now let's have a look at one of the lines. For example, here we have line 1, which is the transition between iron 2 plus and iron 3 plus. Now, if we look at the standard electrode potential for that reaction, we can look up in the Handbook of Chemistry and Physics that it's plus 0.771 volts versus the standard hydrogen electrode potential. And indeed, here you see this line. Now, also you can look at the equation. You don't see here any protons or OH minuses, which means that this line is independent of pH. And that's also why it's straight line. So it doesn't matter whether you're at pH 0 or at pH 4. But clearly you can see that, hey, at higher potentials, apparently there's another state. Now we'll come back to what happens there. So that was the first line. Now let's have a look at the second line here. Another line that's relatively simple is the transition from iron to iron 2, according to this reaction. Also for this reaction you can look up, and its standard equilibrium potential is minus 0.447 volts versus the standard hydrogen electrode. And indeed you find it here at the place where you would expect it. So these horizontal lines are quite straightforward, but you see there are more lines in this Pourbaix diagram that are not horizontal. So how do you get these vertical and basically tilting lines? Now, so let's have a look at line 3, which is a vertical line between iron 3 plus and Fa2O3 with a number of waters. So that is actually not an electrochemical transition. It is a it depends on the solubility of iron 3 in this case. And the fact that it's also not an electrochemical transition makes sense because it's a vertical line, so there's no dependence here on the electrode potential. So it is actually the solubility product that plays a role here. So if you have a high iron 3 concentration, it precipitates as iron hydroxide, which is the same as this Fa2O3 because you have the waters here. And that's what you see. Now, here the solubility product. And now the 10 to the minus 6 turns up, which I mentioned on the previous slide. So iron 3 concentration at 10 to the minus 6. You can fill in the solubility product. We know the solubility constant, we know the iron 3 concentration, and we can deduce then the corresponding OH minus concentration. And this in this case is 1.41 to the 10 minus 11 molar. And now this you can recalculate to a pH, which is 3.15. And that is indeed what we see here, this line 3 vertical at 3.15. So which means that above pH 3.15, the iron 3 plus starts to precipitate. And then the preferred state of the iron is as iron 2O3. Now, let's have a look at one of the more difficult lines in a Pourbaix diagram, namely the tilted lines. Which is, we take this line 4 as an example, which is the transition from the iron 2 plus to the Fe2O3 with the waters with it. That's basically this reaction as we write it down here. So iron oxide, hydroxide plus electrons gives iron 2 plus 3 OH minus. And you can also write the electrochemical, you can basically fill in the Nernst equation, and this is what you get. So we have E is E0 plus RTF ln 1 divided by iron 2 divided by OH minus to the third. The problem is that if you start now to look for the equilibrium standard potential of this reaction, you are not going to find it. Because it's not in a list. But the good news is that we can deduce the E0 for this reaction. So, because we can basically see that there are two reactions occurring together. It's the iron 3 plus electron gives iron 2 plus, and this transition of FaOH3 leads to Fe3 plus and 3 OH minus. It's basically the horizontal line we just discussed and the vertical line we just discussed, and they come together in this overall equation. Now, for this first reaction, we know that the E is E0 plus RTF ln Fe3 plus divided by Fe2 plus. And for the second reaction, we just discussed that the solubility product is Fe3 multiplied by OH minus to the third. That also means that we know from this that the iron 3 concentration is the solubility product divided by the OH minus concentration to the power 3. So now we can start doing things, because now we can basically, what we can do is we have this equation and we have that equation, and we can fill in this iron 3 concentration into the first equation. And then we get this, so we get E is E0 plus RTF ln, so solubility constant, divided by Fe2 plus OH minus to the third. So this is now not the E0 of this first reaction, it's actually the E0 of this reaction. Also, so this also leads to a different equation. Here we did not see the KSP, and here we do see the KSP. So that's the critical difference. Now, what if you you can basically take this equation apart and rewrite it like this, split the natural logarithms into these parts, and then you can fill in all these numbers, because the E0 of the iron 3, iron 2 reaction we know is 0.77. This is a constant because we know the solubility product RT divided by F times the ln results in minus 2.27. Then we know we can fill in the concentration of the iron 2. This is again this 10 to the minus 6, leading to 0.35. And then we can fill in here. Basically, we can replace the OH minus concentration by the pH, and we can then get 0.177 multiplied by 14 minus the pH. And then if you do this together, and I really recommend you to also make this calculation yourself, you get as a result plus 1.33 minus 0.177 multiplied by the pH for the electrode potential. And indeed, if you then look at this line, you can, I have to look a bit, but you can see that, for example, if you make it to the, if you extrapolate this line to the y-axis, that it indeed seems to cut the y-axis at 1.33. So it seems to be correct. So this way you can calculate these more difficult lines in a Pourbaix diagram. So it's quite a calculation. Now, with this, we come to the end of the final screencast of Module 2, and that's then also the moment to look back at what are the key learning lessons of this Module 2. So that's what I want to repeat here. So with electrochemical thermodynamics, we can calculate equilibrium cell potentials, so both the anode and the cathode reaction together. We can also use it to calculate electrode potentials for half reactions. Then we need to make use of this standard hydrogen electrode. And we can use it to predict the stable states of metals from Pourbaix diagrams to help us in selecting electrode materials. And this is where I would like to end the Module 2 on electrochemical thermodynamics. Thank you for your attention.